In the beginning, there was no explosion, no burst of fire or chaos, only a profound transformation. What we now call the Big Bang was not a bang at all, but the unfolding of time itself. It happened not in one place, but everywhere, all at once. In this moment, space itself blossomed from an origin we cannot fully understand, and the universe, once infinitely small, began its endless expansion. What if I told you the Big Bang occurred inside you, inside me, inside every star and void we have ever observed? What if I said this story doesn't start with an explosion, but with an awakening? Welcome to a journey not only through time and space, but through thought, theory, and imagination. This is the story of where it all began and where the known ends. The universe has always stretched our imaginations. Our earliest ancestors looked to the sky and found gods. Now, we find galaxies. But perhaps the greatest myth of all is the one we tell about our origin, the Big Bang. That grand, misunderstood moment in which everything supposedly burst into existence from a single point. The truth is stranger, more intricate, and far more beautiful. For starters, the Big Bang happened not at a single location, but everywhere. It was not an explosion in space, but the expansion of space itself. Imagine a balloon inflating, the surface stretches, but no point on the balloon's skin is the center. Every part recedes from every other part. This is our universe not growing into something, but expanding from within. About 13,800 billion years ago, something extraordinary occurred. Our best theories suggest the entire universe, no matter how large it is, even if it is infinite, was once compressed into a state of unimaginable density and temperature. This wasn't a point in space, it was the beginning of space and time themselves. But this idea, known as a singularity, is a mathematical mirage. It tells us that our equations, powerful as they are, break down at the edge of understanding. The singularity is not a thing. It is a signal, a flare telling us our knowledge falters here, and something deeper remains hidden. Yet out of this uncertainty has come revelation. The expansion of the universe is not a theory, it is an observation. Galaxies are fleeing from us in every direction. The cosmic microwave background, the afterglow of creation, bathes the cosmos in a whisper of ancient heat. Light elements, forged in the first minutes, bear witness to the fire of the past. The Big Bang model, for all its mystery, explains these things better than anything else we have. But questions remain. Why is the universe so uniform in temperature? Why is it so flat, geometrically speaking? And why are there no signs of predicted cosmic relics like magnetic monopoles? These questions plagued physicists until a new idea emerged: inflation. In the beat 1970s, physicist Alan Guth proposed that in the earliest fraction of a second, the universe underwent an immense expansion, growing exponentially faster than the speed of light. This rapid inflation would smooth out temperature differences, erase curvature, and dilute any unwanted relics. A cosmos inflated in this way would look very much like ours. The mechanism behind this inflation, a scalar field, a kind of energy field that permeates all of space. This idea wasn't entirely new. Peter Higgs had introduced a similar concept to explain why particles have mass. But Guth's version gave rise to something incredible, a universe born not in a bang, but in a burst of space itself. As the scalar field rolled down its potential energy curve, it unleashed its stored energy into the fabric of the universe. The result was not just a growing universe, but a hot one. As inflation ended, the field decayed, reheating the cosmos and filling it with the particles we see today: photons, electrons, neutrinos, quarks, and perhaps even the mysterious dark matter. This moment of reheating is, in essence, what we call the Big Bang, not a singular event, but a consequence of a deeper process. The cosmos, born from inflation, found itself teeming with matter, radiation, and the seeds of galaxies. And those seeds, they arose from the quantum foam of the universe itself. Tiny fluctuations in the energy of space, stretched by inflation to cosmic scales, became the scaffolding for all future structure. Stars, planets, and life owe their existence to the whisper of quantum uncertainty in the earliest times. In 2010, the European Space Agency's Planck satellite captured the most detailed image of the cosmic microwave background ever produced. It showed us the echo of the universe's birth and confirmed predictions of inflation with astonishing precision. The scalar spectral index, a measure of those early fluctuations, was found to be just under 1, just as inflation predicted. This was a triumph, a celebration, a moment of champagne and wonder, for in the intricate dance of math and measurement, we had glimpsed the faintest outline of the truth. Inflation, though still incomplete and mysterious, had earned its place in the story of the cosmos. But what if it did not end there? What if inflation did not simply stop, but continues even now, far beyond the edge of our observable universe? What if inflation is eternal? In this picture, our universe is just one bubble in a foaming sea of creation. Each bubble, a universe with its own laws, its own particles, its own destiny. Some are like ours, most are not. This is the inflationary multiverse, a cosmic landscape of infinite possibility. And if that landscape exists, then perhaps the Big Bang was not the beginning, but merely a beginning. The first step, not the whole journey. Beyond the veil of what we can see, the universe may be far more vast, far more varied, and far more strange than we have ever dared to imagine. In the vast stillness beyond what our instruments can measure, there may lie a multitude of realities, worlds within worlds, each born from the same primordial breath that sparked our own. When Alan Guth introduced the idea of inflation, he likely did not foresee how far the consequences would ripple. The original concept, designed to solve a few nagging problems with the Big Bang model, has since unraveled into one of the most profound implications in modern cosmology, that our universe might not be alone. The theory of eternal inflation suggests that inflation is not a one-time phenomenon. Instead, it continues endlessly, eternally, in the fabric of space-time. While inflation may have ended in our own region, allowing galaxies and life to form, other regions continue to swell at unimaginable rates. Within this grand, ever-growing expansion, isolated pockets may randomly emerge where inflation slows and stops, creating bubbles, each bubble a universe. These bubble universes are not like cities on a map. They are entirely separate realms, potentially governed by different physical laws, different particles, and different constants of nature. Some may expand rapidly into nothingness. Others may curl up and collapse. A rare few like ours may strike the delicate balance that allows for complexity, for structure, for life. This is not merely philosophical conjecture. The inflationary multiverse arises naturally from the mathematics of quantum field theory combined with general relativity. The quantum fields responsible for inflation are not smooth and deterministic. They are noisy, chaotic, full of quantum jitter. In some places, the field drops low enough to end inflation and birth a universe. In others, it stumbles and stutters, keeping expansion alive. This randomness breeds diversity. Imagine a vast, foaming sea. Each bubble that rises to the surface bursts into a new cosmos. Most vanish unseen, but ours did not. Our bubble grew and cooled. And from that calm came everything: stars, galaxies, atoms, and consciousness. Yet this vision carries unsettling implications. If the multiverse truly exists, then every possible configuration of matter and energy occurs somewhere, not just once, but infinitely. There are universes where physics never permits atoms to form, others where stars ignite but never die. Somewhere, there may even be a version of you reading this sentence inhabiting a universe nearly identical to ours, save for the smallest, strangest difference. How can we comprehend such vastness? How can we test it? The most straightforward answer is, we can't not directly. Each universe is causally disconnected from the rest. The boundaries between them stretch faster than light, making travel or communication impossible. Even light cannot bridge the gulf. But there may be clues. If our bubble universe collided with another early in its history, that impact might have left scars, circular imprints, in the cosmic microwave background. Astronomers have searched for such marks in the data gathered by the Planck satellite. So far, nothing definitive has appeared, but the hunt continues. Still, skepticism remains. Critics argue that a theory which predicts every outcome predicts nothing. If all possibilities exist, then what does it mean to explain our universe? How do we separate truth from tautology? These are deep questions, philosophical as much as scientific. Yet even if we cannot directly prove the multiverse, the framework of eternal inflation compels us to take it seriously. If inflation occurred and the evidence increasingly supports it, then eternal inflation is difficult to avoid. The quantum nature of fields makes it almost inevitable. This line of reasoning leads to a strange convergence. Theoretical physicists, working from different directions, have found themselves arriving at similar conclusions. Those studying string theory, for instance, have confronted their own overwhelming landscape of possible universes. String theory proposes that the fundamental components of reality are not particles, but tiny vibrating strings. These strings require additional dimensions up to 10 or 11 to vibrate correctly. These extra dimensions, though invisible to us, determine the properties of the universe, and they can curl up in an immense variety of ways. Estimates suggest there may be 10 to the power of 500 possible configurations of these extra dimensions. Each configuration yields different physical laws. One might produce a universe with strong gravity and no stars. Another, like ours, might enable galaxies and DNA. The vastness of this landscape is breathtaking and frustrating. String theorists cannot yet calculate which configuration corresponds to our universe. But if inflation can sample this landscape, if eternal inflation generates universes across the entire range of possibilities, then perhaps our existence makes sense after all. We are here, in this universe, precisely because it is compatible with life, not because it is special or inevitable, but because life can only arise in the rare cosmic environments where the conditions allow it. This is the Anthropic argument: we observe a universe that supports life because we are here to observe it. It may feel unsatisfying, it may feel like surrender, but it could also be the most honest conclusion we can draw. The multiverse does not diminish our place in the cosmos. It reveals how exquisitely rare and precious that place truly is. Each breath we take, each star we see, is a miracle of probabilities. We are a story written in particles and light, carved into the fabric of a universe that may be one of many. Our bubble floats in a sea without shores, surrounded by realms we can never touch. And yet, the story continues. For as long as inflation endures, and it may endure forever, the multiverse blossoms anew. With every quantum twitch, space stirs and spawns. New universes are born with their own tales, their own mysteries, their own versions of wonder. The landscape of reality may be far more vast than we ever imagined, not just in space, but in the very rules that govern existence. String theory began not as a cosmic theory of everything, but as a modest attempt to explain a curious pattern in particle physics. But as the equations expanded and the implications unfolded, something unexpected emerged, a path toward unifying all the known forces of nature, including gravity, within a single, elegant framework. In string theory, what we perceive as particles, electrons, quarks, photons are not point-like dots, but tiny vibrating loops of energy. Each type of particle corresponds to a different vibrational mode, much like the strings of a violin producing different notes depending on how they vibrate. This simple shift in perspective opens up profound possibilities. But to accommodate these vibrations, string theory requires more than just the familiar 3 dimensions of space. It demands additional spatial dimensions, 6 or 7, depending on the version of the theory. These extra dimensions are not visible to us because they are curled up at scales far smaller than we can observe, compactified into intricate shapes that defy easy visualization. These compactified dimensions can fold and twist in an almost limitless number of ways. Each unique configuration, each way of curling the extra dimensions, determines the vibrational properties of strings, and thus the physical laws of a universe. Change the shape, and you change the laws. The strength of gravity, the behavior of electromagnetism, the mass of particles, everything shifts. The number of possible configurations is staggering 10 to the power of 500 or more. Each represents a distinct universe with its own internal logic, its own constants, its own potential for complexity or simplicity. Most of these universes are probably sterile, lifeless, perhaps even devoid of atoms. But among the vast tapestry, a few may be like ours. This collection of all possible configurations is what physicists call the string theory landscape. It is not a place, but a mathematical space of possibilities. And here is where string theory meets eternal inflation. Eternal inflation populates this landscape. Each time inflation slows and a bubble universe forms. That bubble can settle into a different point on the landscape. That is, the way the extra dimensions compactify during the end of inflation determines which version of physical laws that universe inherits. Over cosmic time, inflation could sample vast swaths of the string landscape, generating a multiverse rich in diversity. This convergence of ideas gave birth to a bold proposal. Perhaps we do not need a reason why our universe has the properties it does. Perhaps it is not chosen, not designed, but simply one possibility among many. We live here because here allows us to live. This is the Anthropic principle extended to the multiverse of all the possible universes. We find ourselves in one of the few where observers can exist. Some physicists recoil from this idea. It seems to abandon the dream of a unique, deterministic theory of everything. If any outcome is possible, and all outcomes exist somewhere, what's the point of explanation? But others see it differently. They argue that the vastness of the landscape is not a flaw. It is a feature. It reflects the richness of a reality not bound by our preconceptions. The multiverse offers a mechanism to realize the potential of the string landscape. Each universe becomes a note in a cosmic symphony, each one shaped by the geometry of dimensions too small to see but too powerful to ignore. And our universe, our melody, is one that permits stars to shine, planets to form, and consciousness to emerge. But even within this grand idea, there are limits. We do not know how to calculate the precise connection between the shape of the extra dimensions and the physics we observe. The mathematics is daunting. The equations are unyielding. For now, the landscape remains a map without a legend, a terrain glimpsed but not fully charted. Still, progress continues. Physicists attempt to simplify, to find patterns, to uncover whether certain configurations are more likely than others. They searched for universal features, properties that emerge again and again across the landscape. Perhaps these can give us clues as to why our universe is the way it is. And in this endeavor, something remarkable has occurred. Ideas from string theory, eternal inflation, and cosmology have begun to merge into a unified narrative. What began as abstract mathematics now touches the very question of existence. We are no longer asking just what the universe is made of, but why it is made this way at all. Let us imagine, for a moment, that the string landscape is real, and that eternal inflation populates its myriad possibilities. Each bubble universe forms, evolves, and dissolves according to its own local laws. But even this grandeur begs a deeper question. Where did the landscape itself come from? Why does it exist at all? Why should the equations of string theory, or quantum fields, or inflationary dynamics be true? What placed them there? Physics excels at answering the how, not the why. Yet as we push further into the prehistory of the cosmos, we can no longer avoid the philosophical. The deeper we search, the more elusive the foundation becomes. And in this terrain of speculation, new ideas arise, bold alternatives that challenge everything we thought we knew about beginnings. In 2001, a radical model emerged from the minds of Justin Coury, Bert Ovrutt, Paul Steinhardt, and Neil Turok, anchored in string theory but abandoning inflation. Their theory proposed that our universe is one of two vast three-dimensional membranes or branes floating within a higher dimensional space. Most of what we call the universe is confined to this brane, including all known particles and forces except gravity. In this model, known as ekpyrotic cosmology from the Greek word for conflagration, the Big Bang was not the beginning but the result of a collision. Another brane, traveling through the hidden dimensions, smashed into ours. The impact released colossal energy, heating the universe and initiating what we perceive as the Big Bang. Unlike inflation, which smooths the cosmos by rapid expansion, ekpyrosis achieves the same by compressing it beforehand. The model even allows for cyclic behavior. The branes could separate and collide again and again, each impact triggering a new round of cosmic creation. This is a universe without beginning, without end, reborn eternally in a rhythmic dance of collision and fire. Other ideas push even further. Loop quantum gravity, a competing approach to unifying general relativity with quantum mechanics, suggests that space itself is not continuous but made of discrete units, tiny quanta, of volume. These units form a kind of network, like pixels on a cosmic screen. In this framework, singularities, points of infinite density, are not physical realities, but mathematical mirages. According to loop quantum cosmology, our universe may have emerged from a previous phase. Instead of a Big Bang, there was a big bounce, a contracting universe, governed by quantum gravity, reached a minimum size, then rebounded into expansion. Time did not begin at the bang, it simply reversed direction. This avoids the singularity problem and provides a mechanism for a universe that cycles endlessly through expansion and contraction. Still more speculative is Roger Penrose's conformal cyclic cosmology. Here, the end of one universe is the beginning of the next, as the cosmos expands and cools toward an empty, entropy-maximized state. The scale of space becomes irrelevant. Without mass or structure, time loses meaning. This final state becomes indistinguishable from the ultra-dense beginning of a new Big Bang. One eon gives birth to another, connected not by matter, but by the mathematics of geometry. These visions are dazzling, but they share one thread and attempt to make sense of the beginning by eliminating it. In each, the cosmos is eternal, not in the static, unchanging way of ancient philosophy, but in a dynamic, evolving cycle where the beginning is always born from an end. There is no singular origin, only a series of transformations. But even here, the mystery deepens. For all these models require laws. They require mathematical structures, rules that govern quantum fields, brains, or spin networks. They require something. And so the question returns, why is there something rather than nothing? This is not merely a question of physics, it is a question of ontology, of existence itself. Why do laws exist? Why does logic hold? Why can anything be, rather than not be? Some thinkers propose that the laws of physics are themselves emergent, arising from deeper principles of information, entropy, or computational complexity. Others imagine a deeper law of laws, a meta-rule from which all structure flows. And then there are those who suggest that perhaps nothingness is unstable. Perhaps existence is inevitable not because it was caused, but because it is the default. In a quantum sense, nothing is not empty. It is a teeming sea of possibilities. And from this sea, something must eventually emerge. In quantum field theory, particles appear spontaneously out of the vacuum, provided they vanish quickly enough to preserve conservation laws. Could the universe itself be such a fluctuation? A temporary bubble of being within an infinite void? Perhaps. But then what is the void? We stand here, conscious creatures in a cosmos full of structure and light, asking questions that may have no answers, or perhaps the answers lie beyond our current grasp, concealed in mathematical patterns yet unwritten, or woven into the very fabric of thought and observation. To seek the origin of everything is to challenge the limits of reason itself. We rely on causality, on time, on the structure of logic, but at the foundation of all things, these may dissolve. The origin of the universe may be the origin of time. Before that, the very notion of before may be meaningless. Yet we continue to ask, and that, perhaps, is the most human act of all. To understand the origin of time, we must first understand what time is. In Newtonian mechanics, time is absolute, a universal backdrop against which motion plays out. In Einstein's relativity, time is flexible, inseparable from space, bending in the presence of mass and energy. In quantum mechanics, time is not an operator, but a parameter, a ticking clock that tracks changes in a system. These views, though each powerful, are mutually incompatible. General relativity and quantum mechanics are the twin pillars of modern physics, but they tell different stories about time. In one, time flows through a curved space-time fabric. In the other, it is a label on a probability wave. Reconciling these two pictures has been one of the greatest challenges in theoretical physics. As we approach the Planck epoch, the first instant after the beginning, the predictions of both theories break down. Gravity becomes as strong as quantum effects, and space-time itself becomes turbulent, foaming, a quantum soup. Here, classical notions of before and after may no longer apply. This is the realm of quantum gravity, a theory not yet complete, but actively pursued. In many formulations, time is not fundamental, it is emergent. It arises from correlations between events, from entanglement, from patterns in quantum states. In such a view, time did not exist before the universe, it arose with it, like a melody that emerges when the first note is played. Some physicists argue that causality, the idea that one thing leads to another, may also be emergent. In a timeless quantum world, the future and past are illusions, artifacts of human perception. There is only a vast, static structure of possibility, and what we call history is merely a path through it. And so the question what happened before the Big Bang may be meaningless. If time began at the Big Bang, then there was no before. The universe did not emerge from something, it emerged from nothing, not as a thing in space, but as space itself coming into being. Still, human minds crave explanation. We invent myths, draw equations, build colliders to smash particles together and peer into the deep past. But every answer brings another question. If the laws of physics gave rise to the universe, what gave rise to the laws? If time emerged from quantum fluctuations, why do such fluctuations exist? What breathes fire into the equations and makes them real? These are questions that push the edge of knowability. They are the boundary stones of science, and they invite humility. For perhaps the ultimate origin, the reason for existence itself lies forever beyond the reach of mathematics or experiment. Perhaps it can only be felt, not proved. Or perhaps we are standing on the shore of a deeper truth, waiting to discover tools we do not yet possess, concepts we have not yet imagined. One day, a unifying theory may rise that explains quantum gravity, the birth of time, and the emergence of law, or perhaps not. What we do know is this: the universe is old and vast, but we are young and curious. We are the thinking part of the cosmos, the self-aware fragment seeking to know the whole. We are atoms that ask where atoms came from. We are beings shaped by time, yearning to understand time's origin. And that journey, the search itself, is perhaps the greatest story of all. Not because it answers everything, but because it dares to ask. We may never know why there is something rather than nothing, but we can marvel that there is anything at all. So, as we close this story, remember that the cosmos does not end in understanding. It begins there, with every new discovery, with every new idea, with every new question we dare to ask. The universe expands not just in space, but in meaning.
What would it feel like to stand in the loneliest corner of the universe? To gaze into an endless void, devoid of stars, planets, and even the faintest whispers of light? What stories does the great nothing hold? And what secrets does it whisper about the cosmos we call home? Close your eyes and picture yourself within a supervoid, an incomprehensibly vast expanse of near-total emptiness. Darkness surrounds you, not merely as a shadow or a veil, but as an all-encompassing abyss. If you could peer across this cosmic desert, even armed with the sharpest amateur telescope, you would see nothing. No stars, no faint galactic smudges to hint at a greater universe beyond. To you, the cosmos itself would seem barren. Now imagine standing at the edge of the boat's void, a titanic spherical emptiness spanning 330 million light-years across, a chasm so immense that the Milky Way could fit within it millions of times over. Within this colossal volume, where thousands of galaxies should reside, astronomers have discovered only a handful, scattered like solitary embers in an extinguished fire. As astronomer Greg Aldering noted, had the Milky Way been in its center, humanity might not have known other galaxies existed until the mid-20th century. This great nothing defies our understanding of the universe's architecture. Theories about cosmic structure growth tell us that voids, the gaps between galaxy clusters, should span no more than tens of millions of light-years. Yet the boat's void, with its staggering scale, shatters these expectations, challenging our grasp of how the cosmos has evolved. It offers a window into the universe's early days, revealing clues in its sparse, tube-shaped galaxies, perhaps remnants of a primordial wall crumbling between neighboring voids. Even in the bleakest recesses of space, light persists, carrying with it the stories of creation and destruction. But to find true darkness, complete and utter nothingness, we must travel even further back in time, to an era forebodingly named the Cosmic Dark Ages. This was a time before stars ignited, before galaxies formed, and before any light illuminated the universe's tapestry. For 200 million years after the Big Bang, the universe lay shrouded in total darkness, a long and mysterious slumber. Why did it take so long for light to emerge? What does this prolonged night reveal about the stars and galaxies we see today? And most importantly, how can we illuminate a time when the universe itself was unlit? Throughout history, humanity has confronted humbling truths. Copernicus revealed that Earth was not the center of the solar system, or discovered that the Sun was not the center of our galaxy. Hubble unveiled a universe teeming with galaxies, each a world unto itself. Slowly but surely, we've learned that we are not the center of anything. The Great Nothing and the cosmic voids like it remind us once again of our place in the vast, silent expanse of the cosmos. Yet, within this silence, there is beauty. Even in the deepest voids, the universe speaks to those who dare to listen. What lies hidden in the vast, impenetrable darkness of the universe? Can we ever hope to unveil the secrets of the cosmos, the stories written in the faintest whispers of ancient light? How do we peer beyond the stars and galaxies to touch the very fabric of time, to witness the birth of the first structures in existence? These are the questions that drove astronomers to the edge of their imaginations, to take a billion-dollar gamble on one of the most ambitious observations in the history of science. In 1995, Bob Williams, then director of the Hubble Space Telescope Science Institute, found himself at a crossroads. Holding the reins of the world's most powerful telescope, he had reserved personal observing time, a rare privilege that made him the envy of his peers. Yet Hubble was not without its controversies. The telescope, launched in 1990 at a cost of billions, had initially delivered blurry images due to a flaw in its primary mirror. This flaw, an aberration smaller than 1/50th the width of a human hair, caused incoming light to focus improperly, clouding its view of the cosmos. For many space missions, such a defect would have been a death sentence. But Hubble's low Earth orbit made it uniquely repairable. In 1993, astronauts aboard the Space Shuttle Endeavour executed a daring repair mission, installing corrective optics that restored Hubble's vision. Now, with the telescope's capabilities fully realized, the pressure was on to produce results that justified the expense and effort. Williams, against the advice of many colleagues, made a bold decision. He pointed Hubble at what seemed to be an empty patch of sky, a region devoid of stars, galaxies, or any visible structure. This patch, just 1/30th the diameter of the Moon, became the focus of 10 continuous days of observation. To the naked eye and previous telescopes, this patch of sky appeared barren, an unremarkable void. But Hubble's unprecedented sensitivity and resolution slowly gathered photons from the faintest and most distant objects in the universe. Over the long exposure, shapes began to emerge in the darkness. The result was the Hubble Deep Field, an image that transformed our understanding of the cosmos. Thousands of galaxies appeared, each a swirling island of stars, gas, and dust, scattered across a seemingly empty void. These galaxies varied in size, shape, and color, painting a vivid portrait of the universe's history. The significance of the Hubble Deep Field extends far beyond its aesthetic beauty. This image is a two-dimensional projection of a three-dimensional universe. Galaxies that appear to be neighbors in the image are, in reality, separated by vast distances. Moreover, it is a projection of time. The light from these galaxies has traveled for billions of years to reach us, meaning we see them as they were in the distant past. The farther a galaxy, the older the light we observe. This phenomenon allows us to construct a timeline of cosmic evolution, peeling back layers of time to glimpse the universe as it was only hundreds of millions of years after the Big Bang. To understand this concept, consider the observable universe as a series of concentric shells around us. The nearest shell includes objects like the Sun, whose light takes about 8 minutes to reach Earth. A slightly more distant shell includes our neighboring galaxy, Andromeda, whose light takes 2.5 million years to arrive. This light was emitted when early human ancestors, such as Homo habilis, roamed the Earth. As we move farther out, the light we observe grows progressively older. By examining these ancient photons, we can study the universe at different stages of its history. Hubble's deep field observations revealed galaxies from an era only a few 100 million years after the Big Bang. These galaxies are so distant and faint that they appear as red smudges, their light stretched to longer wavelengths by the expansion of the universe. This phenomenon, known as redshift, is akin to the Doppler effect we observe with sound. Just as the pitch of a siren changes as it moves toward or away from us, the wavelength of light changes depending on the motion of its source. A galaxy moving away from us appears redder because its light waves are stretched. By measuring the redshift of galaxies, astronomers can calculate their distances and speeds, effectively mapping the universe in both space and time. Edwin Hubble, the telescope's namesake, discovered in the 1920s that galaxies are receding from us and that their velocities increase with distance. This relationship, known as Hubble's law, is a cornerstone of the Big Bang theory. It implies that the universe is expanding, with galaxies moving apart like dots on the surface of an inflating balloon. The most distant galaxies observed by Hubble are also the oldest, their light carrying the imprint of a universe in its infancy. The latest advancements in observational astronomy have pushed this frontier even further. The James Webb Space Telescope, JWST, launched in 2021, has taken deep field imaging to new heights. Its powerful infrared capabilities allow it to peer through cosmic dust and capture even fainter redshifted galaxies. One of JWST's deep field images revealed thousands of galaxies within an area of sky no larger than a grain of sand held at arm's length. These observations have brought us closer than ever to the epoch of the first stars, a time when the universe transitioned from darkness to light. The earliest era of the universe, known as the cosmic dark ages, predates the formation of stars and galaxies. For approximately 200 million years after the Big Bang, the universe was a dark, featureless expanse of hydrogen and helium. Although these elements contained the seeds for star formation, no light emerged during this time. The cosmic dark ages represent a frontier that even the most advanced telescopes cannot penetrate, as there was no visible light to detect. This raises profound questions. Why did the universe remain dark for so long? What processes eventually sparked the formation of the first stars? And can we ever hope to study this enigmatic epoch? In the earliest moments of the cosmos, light was the supreme ruler of the universe. The energy density of radiation far exceeded that of matter, creating a dynamic environment where photons frequently collided with particles, preventing the formation of stable atoms. The universe at this stage was a superheated plasma, a cauldron of particles and radiation so intertwined that photons were scattered and absorbed almost as quickly as they were emitted. The cosmos was vibrant, chaotic, and entirely opaque to the naked eye. But the balance of power between radiation and matter was not to last. As the universe expanded, its volume increased, and both radiation and matter thinned out. However, the energy density of radiation fell more rapidly due to an additional factor, cosmological redshift. The universe's expansion stretched the wavelengths of photons, reducing their energy and equivalent temperature. This meant that while matter continued to dominate gravitationally, the power of radiation waned. Approximately 380,000 years after the Big Bang, the universe reached a pivotal threshold. The energy density of matter surpassed that of radiation. Light's dominion over the cosmos ended, giving way to a new era. At this point, the temperature of the universe had cooled sufficiently for a remarkable transformation to occur. Atomic nuclei, which had been unable to hold onto electrons due to the incessant bombardment of high-energy photons, could now form stable atoms. This process, known as recombination, marked the beginning of a transparent universe. Freed from the constant interactions with electrons and nuclei, photons could now travel vast distances uninterrupted. For the first time, light was free. But what would this newfound freedom look like to an observer in this early universe? The answer lies in the nature of the radiation emitted during recombination. The photons at this time formed a blackbody spectrum, radiating across a range of wavelengths determined by the temperature of the universe. To an observer, the cosmos would have appeared suffused with a warm orange glow. Over the ensuing millions of years, as the universe continued to expand and cool, this glow would redden, fading from the visible spectrum entirely as the radiation shifted into the infrared, microwave, and radio wavelengths. Eventually, the universe's once vivid light faded into the background, becoming the cosmic microwave background, CMB, that we detect today. Darkness fell across the cosmos. Yet even in this profound darkness, the universe was far from silent. Another kind of matter, forged during the Big Bang, played a critical role in shaping the cosmos: dark matter. Unlike the familiar matter that makes up stars, planets, and galaxies, dark matter does not interact with electromagnetic radiation. It neither absorbs nor emits light, making it invisible to conventional observation. Its presence is revealed only through its gravitational influence. The enigmatic nature of dark matter began to emerge in the 1960s when astronomers Kent Ford and Vera Rubin made a groundbreaking discovery. By measuring the orbital velocities of stars within spiral galaxies, they uncovered a perplexing anomaly. Stars at the edges of galaxies were moving far too quickly to be accounted for by the gravitational pull of visible matter alone. According to the laws of gravity, stars moving at such speeds should have escaped their galaxies entirely, yet they remained bound. The only plausible explanation was the existence of a vast, unseen component of mass: dark matter. Calculations suggest that dark matter constitutes about 85% of all matter in the universe, yet it eludes direct detection. Unlike ordinary matter, which interacts both gravitationally and electromagnetically, dark matter interacts solely through gravity. This lack of electromagnetic interaction means it cannot radiate away energy, a property that profoundly shapes its behavior. As the universe expanded and cooled, regions of dark matter began to collapse under their own gravity, forming dense structures known as halos. However, the collapse of dark matter is limited by a critical factor: the absence of a mechanism to dissipate heat. In ordinary matter, particles within a collapsing cloud can convert their kinetic and thermal energy into electromagnetic radiation. This radiation escapes, allowing the cloud to cool and collapse further. This process ultimately leads to the formation of stars and planets. Dark matter, by contrast, cannot emit photons. Without this escape valve, the outward pressure from particle motion balances the inward pull of gravity, halting the collapse before stars or planets can form. Instead, dark matter organizes into an intricate web of filaments, connecting at dense nodes to form halos. This cosmic web became the scaffolding upon which visible matter would later accumulate. At the time of recombination, the universe was a tapestry of dark matter filaments, shrouded in a uniform glow of cooling radiation. To an observer, the dark matter would remain invisible, hidden behind the warm orange and red hues of the plasma. As the glow faded and the universe entered its first prolonged darkness, the dark matter continued to shape the cosmos in silence, providing the gravitational framework for the next chapter of cosmic evolution. For nearly 200 million years after recombination, the universe remained in this state of equilibrium. The dark matter web persisted, and the primordial gas, composed mostly of hydrogen and helium, was too diffuse to ignite fusion. The cosmos was a vast, dark expanse of potential, but no stars illuminated the void. This era, often referred to as the Cosmic Dark Ages, posed a profound question: how did the universe break free from this impasse to form the first stars? The answer lies in the subtle interactions and dynamics of matter within the gravitational wells of dark matter halos. As gas accumulated within these wells, its density increased. Under the relentless pull of gravity, regions of gas began to collapse. Despite the challenges posed by dark matter's inability to cool, ordinary matter could dissipate energy through radiative processes. Slowly, these collapsing gas clouds reached the critical conditions necessary for nuclear fusion. The first stars, known as population 3 stars, ignited, flooding the universe with light and ending the cosmic dark ages. These stars were unlike any that exist today. Formed from primordial gas, they lacked heavy elements and were massive, short-lived, and intensely bright. Their light reionized the surrounding gas, creating bubbles of ionized hydrogen that expanded and merged. This process, known as reionization, marked the universe's transition from darkness to illumination, setting the stage for the formation of galaxies and the complex structures we observe today. But how do we, as observers in the present day, uncover the secrets of an era so deeply shrouded in darkness? While the first stars and galaxies are beyond the reach of direct observation, their imprints linger in the universe's structure and radiation. The CMB provides a snapshot of the universe at recombination, offering clues about the distribution of matter, including dark matter. The large-scale structure of the universe, mapped through surveys of galaxies, traces the underlying dark matter web. Advanced telescopes like the James Webb Space Telescope are pushing the boundaries of observation, capturing the faint light of the earliest galaxies and providing insights into the processes that shaped the cosmos. 1937. The skies above New Jersey were illuminated not by the graceful flight of the German airship Hindenburg, but by its fiery demise. The pride of a fleet that symbolized the marvels of human engineering was consumed in a catastrophic blaze as it attempted to dock. The hydrogen-filled cells that provided its buoyancy became its downfall. As the gas escaped, mixing with oxygen in the air, a spark, likely static electricity, ignited the mixture, setting off a chain reaction that engulfed the massive airship in flames. Remarkably, nearly 2/3 of the passengers and crew survived, largely due to the airship's proximity to the ground and the relatively prolonged duration of the disaster. Yet the tragedy claimed 35 lives and left an indelible mark on aviation history, effectively ending the era of airships as a mode of transportation. The Hindenburg disaster underscored the dual nature of hydrogen, its simplicity as the lightest and most abundant element in the universe, and its potential for immense destruction. Hydrogen's flammability made it a dangerous choice for airship propulsion, but its simplicity, one proton and one electron, belies its profound power. This same element, under the right conditions, powers the sun and fuels the most devastating weapons ever conceived by humanity. The hydrogen bomb, which relies on nuclear fusion, can release energy thousands of times greater than fission-based bombs. While such weapons have thankfully never been used in warfare, their existence serves as a stark reminder of the energy locked within this seemingly innocuous element. At the same time as hydrogen's destructive potential was being harnessed, it became the focus of another scientific pursuit, one aimed not at destruction, but at unlocking the secrets of the cosmos. Astronomers began to recognize hydrogen's critical role in understanding the structure of the universe. Among them was Jan Oort, a visionary who reshaped our understanding of the Milky Way. By the 1930s, Oort had already made a name for himself by demonstrating that the Sun was not at the center of the Milky Way, but instead resided about 30,000 light-years from the galactic core. He showed that the galaxy rotated in a spiral pattern, a discovery that provided critical insights into its structure. However, his work was far from complete. The Milky Way, like many galaxies, is shrouded in vast clouds of interstellar dust that obscure its true form. To map the galaxy's structure accurately, Oort needed a way to see beyond the visible light spectrum, which is easily scattered and absorbed by these dust clouds. The answer lay in radio astronomy. Radio waves, with their long wavelengths, can penetrate interstellar dust, revealing what optical telescopes cannot. This realization coincided with advances in understanding the radio emissions from interstellar space. During World War II, the exchange of scientific knowledge became fraught with risk, particularly for researchers like Oort, who had protested the dismissal of his Jewish colleagues and retreated to a quiet life in the Dutch countryside. But his passion for understanding the galaxy remained undiminished. In 1944, Oort read a smuggled issue of the Astrophysical Journal that hinted at the promise of detecting radio waves from the Milky Way. He immediately saw the potential for a breakthrough. Oort hypothesized that interstellar gas, particularly hydrogen, could emit radio waves. This gas, which feeds the stellar nurseries where new stars are born, might illuminate the galaxy on a grand scale if its emissions could be detected. To test this idea, Oort enlisted a young student, Hendrik Christoffel van der Hulst, to investigate the problem. Van der Hulst's task was to identify a specific radiospectral line associated with hydrogen that could be used to map the Milky Way. Atoms emit light through various mechanisms, most commonly when electrons transition between energy levels. These transitions release photons with specific energies corresponding to particular wavelengths of light. The challenge for van der Hulst was to find a transition that was both common enough to occur across the galaxy and intense enough to be detectable. He meticulously analyzed the atomic transition probabilities of hydrogen and eventually identified a candidate, the hyperfine transition of neutral hydrogen, which occurs when the spins of the proton and electron within a hydrogen atom flip relative to each other. This transition releases a photon with a wavelength of 21 centimeters, corresponding to the radio portion of the electromagnetic spectrum. This discovery was monumental. The 21 centimeter line provided a unique and powerful tool for probing the Milky Way. Unlike optical light, which is absorbed by interstellar dust, the 21 centimeter radio waves could travel unobstructed through the galaxy. Moreover, the widespread presence of neutral hydrogen meant that this emission line could be used to map the distribution of gas throughout the Milky Way, revealing its spiral structure in unprecedented detail. Within the humble hydrogen atom lies a subtle yet profound phenomenon, the hyperfine structure of its lowest energy level. This structure is a result of the interaction between the spins of the atom's proton and its orbiting electron. If the two spins align, the atom occupies a slightly higher energy state. When the spins are opposite, the energy state is lower. Occasionally, and quite rarely, the electron spontaneously flips its spin, transitioning from the higher to the lower energy state. This event, known as a spin flip transition, releases a photon with a specific energy equal to the difference between these two states. This emitted photon has a frequency of precisely 1,420 megahertz, corresponding to a wavelength of 21 centimeters. This falls within the low-frequency domain of the electromagnetic spectrum, making it ideal for detection by radio telescopes. Hendrik van der Hulst first proposed that this 21 centimeter emission line could be the key to mapping hydrogen gas across the Milky Way. Such an endeavor promised to unveil the structure of our galaxy beyond what visible starlight could reveal, providing an extraordinary second sight into the cosmos. Yet, this ambitious idea faced significant challenges. The probability of an electron undergoing a spin-flip transition is astonishingly low. For this rare event to be detectable, the volume of hydrogen emitting these photons needed to be immense. The skeptics compared it to finding a rare trading card in a single pack, exceedingly unlikely. However, with enough hydrogen spread across the vastness of space, these elusive signals could potentially become observable. Still, in the mid-20th century, the astronomical community harbored doubts about whether the cosmos contained sufficient hydrogen to make the 21 centimeter line practically detectable. Undeterred, Jan Oort salvaged a pair of German antennas and set out to construct a device capable of detecting this spectral line. However, while Oort's expertise in astronomy was unmatched, he lacked the electrical engineering skills necessary to build a working radio telescope. Across the Atlantic, a group of physicists led by Edward Purcell and his student Harold Doc Ewan had independently become interested in van der Hulst's theoretical work. Purcell's background in subatomic matter and Ewan's expertise in radar physics gave them the technical edge to pursue the detection of the 21 centimeter line. On Easter morning in March 1951, Ewan and Purcell achieved a historic breakthrough. They successfully detected the 21 centimeter line of hydrogen emission from the Milky Way. Van der Hulst's prediction was vindicated, and the discovery marked a turning point in radio astronomy. Following this achievement, a collaborative exchange of knowledge began between the American and Dutch teams. The Americans shared their expertise in constructing the experimental apparatus, while the Dutch provided the broader astronomical context of the findings. Within months, the global radio astronomy community was equipped to map the hidden structures of our galaxy. By observing the 21-centimeter spectral line, astronomers could identify not only the location of hydrogen gas, but also its motion. The redshift or blue shift of the spectral line indicated whether the gas was moving away from or toward the observer, revealing the dynamics of the Milky Way. This method conclusively demonstrated that the Milky Way is a spiral galaxy, rotating with a complex, organized structure. It also allowed astronomers to trace the galaxy's farthest arms and branches, painting an ever clearer picture of our home in the cosmos. The implications of this discovery extended beyond the Milky Way. Hydrogen is the simplest and most abundant element in the universe, forming the primary component of ordinary matter. Before stars, planets, and galaxies emerged, the universe was filled with diffuse hydrogen gas. This gas became gravitationally bound to the filaments and halos formed by dark matter, tracing the unseen scaffolding of the cosmos. During the cosmic dark ages, the epoch after recombination, but before the formation of the first stars, this hydrogen gas lay hidden in the darkness, invisible to optical telescopes. The 21-centimeter line offers a way to illuminate this hidden universe. Unlike visible light, which cannot penetrate the vast distances and obscuring matter of early cosmic history, 21-centimeter radiation travels unimpeded. Modern radio telescopes can detect this signal, revealing the distribution and movement of hydrogen gas during the universe's formative epochs. Simulations show that hydrogen gas closely follows the structure of dark matter, forming a cosmic web of filaments and nodes. These structures, initially invisible to optical instruments, become strikingly apparent in the radio spectrum. This capability transforms our understanding of the early universe. By observing 21-centimeter radiation, astronomers can trace the environment where the first stars and galaxies began to form. Even during the cosmic dark ages, when no visible light existed, the universe was far from dormant. It was a time of construction, with hydrogen gas slowly accumulating in regions of high density, preparing to ignite the first stars. The 21-centimeter line provides a window into these nascent environments, allowing us to study the conditions that gave rise to the first sources of light. But does the emergence of the first stars truly mark the end of the Dark Ages? The transition from darkness to light was not instantaneous. The first stars, known as population 3 stars, were massive and short-lived, creating bursts of illumination in an otherwise dark universe. As these stars ended their lives in supernovae, they enriched the surrounding gas with heavier elements, setting the stage for the formation of later generations of stars and galaxies. Yet the universe remained patchy, with regions of light interspersed with vast expanses of darkness. Our planet's oceans and seas are a microcosm of the challenges the universe faced during its formative dark ages. They are vast, mysterious, and brimming with life, much of which remains hidden from our eyes. At shallow depths, sunlight reveals schools of vibrant fish, their colors dancing in the refracted light. But as we dive deeper, sunlight is steadily absorbed. Reds, oranges, and yellows vanish by 10 meters, leaving behind only a fraction of the surface brightness. By 50 meters, even greens and violets are excised, and a monochromatic world emerges. Deeper still, at 200 meters, the twilight zone begins, a realm of dim light punctuated by bioluminescent creatures creating their own faint glows. By 300 meters, darkness reigns, interrupted only by moonlight filtering faintly from above. At 850 meters, this light fades entirely, and we enter the midnight zone, where life continues in utter blackness, adapting to an environment beyond human sight. The universe's dark ages echo this story of hidden complexity. While our oceans are veiled in shadow, they teem with life, and so too was the universe during its early epochs, shrouded in darkness, but rich with structure and potential. After the Big Bang, by around 200 million years, gravity began its quiet, relentless work. Dense pockets of hydrogen gas collapsed under their own weight, igniting the first stars. In every direction, faint points of light blinked on, marking the end of the Dark Ages. Yet this light did not flood the universe unimpeded. It battled an ocean of hydrogen that absorbed and muffled its nascent cries. These first stars initiated a profound transformation, but they also illuminated questions that linger to this day. Was the universe's early darkness truly empty? Was it devoid of all light, or was it only dark in the optical wavelengths visible to human eyes? To answer these questions, we must explore the mechanisms by which the first light emerged and interacted with its surroundings. The universe's earliest stars were born in dense pockets of hydrogen gas, the simplest and most abundant element in existence. These stars, known as population 3 stars, were unlike any that followed. Formed from primordial gas, they contained no heavy elements, just hydrogen and helium, and were massive, bright, and short-lived. Their formation marked the first engines of nuclear fusion, where hydrogen nuclei combined to form helium, releasing immense energy in the process. These stars emitted light across the electromagnetic spectrum, from ultraviolet to infrared, but much of this light struggled to escape its birthplace. Hydrogen gas is a voracious absorber of light, particularly at specific wavelengths. The first stars emitted photons in a full rainbow of colors, but hydrogen atoms absorbed specific wavelengths, red, cyan, blue, and violet, creating dark gaps in their spectra. Despite these gaps, the visible spectra of these stars appeared largely intact to an observer. However, the ultraviolet light emitted by these stars encountered a more significant obstacle. It carried enough energy to ionize hydrogen atoms, stripping electrons from their nuclei and transforming the gas into a plasma. This process of ionization marked the beginning of a new epoch, the era of reionization. During this time, the first stars and galaxies began to ionize their surroundings, creating bubbles of ionized hydrogen in an otherwise neutral universe. Each star or galaxy formed its own ionized region, and as these regions expanded, they merged, gradually transforming the universe into the ionized state we observe today. However, this process was far from uniform or instantaneous. The early universe resembled a cosmic Swiss cheese, with pockets of ionized gas interspersed among vast regions of neutral hydrogen. The exact mechanisms driving reionization remain one of cosmology's great mysteries. The first stars were too few and too short-lived to fully ionize the universe on their own. Instead, it is likely that the first galaxies, teeming with second-generation stars and powered by central black holes accreting matter, played a crucial role. These galaxies emitted copious amounts of ultraviolet radiation, steadily expanding the ionized regions until, roughly 1 billion years after the Big Bang, the process was complete. By this time, light could travel freely across the cosmos, marking the true end of the Dark Ages. Despite the monumental importance of the era of reionization, our understanding of this epoch is fragmentary. Observationally, it is a missing chapter in the universe's history. The James Webb Space Telescope, launched in December 2021, has begun to bridge this gap by observing some of the earliest galaxies, providing invaluable insights into the state of the universe during this time. Webb's infrared capabilities allow it to detect light that has been redshifted, stretched to longer wavelengths by the expansion of the universe, making it possible to see galaxies as they appeared just 350 million years after the Big Bang. However, even JWST has its limits. While it can peer deep into the past, it is fundamentally an infrared telescope, restricted to observing galaxies whose light has not redshifted entirely out of its detectable range. To reach further back, into the heart of the Dark Ages, we need to turn to a different tool: radio astronomy. The hydrogen that pervaded the early universe holds the key to probing the Dark Ages. As discussed earlier, hydrogen atoms occasionally emit radiation at a specific wavelength, 21 centimeters. This emission occurs due to the hyperfine transition of hydrogen's electron spin, a rare event, but one that provides a powerful tool for mapping the universe's hydrogen distribution. In the early universe, before the first stars formed, hydrogen gas was abundant and neutral, emitting faint 21 centimeter radiation. As stars and galaxies began to form, they ionized the surrounding hydrogen, creating voids in this signal. By observing the 21 centimeter line, astronomers can trace the progress of reionization, mapping the cosmic web of ionized bubbles and the neutral hydrogen that lies between them. Radio telescopes, such as the Square Kilometre Array (SKA) under construction, are designed to detect these faint signals. By capturing the redshifted 21-centimeter radiation from the early universe, they can reveal the structure and evolution of hydrogen gas during the Dark Ages and the era of reionization. This approach allows astronomers to study not individual stars or galaxies, but the large-scale patterns that define the universe's earliest epochs. Detecting the 21-centimeter signal is a formidable task. The signal is incredibly faint, buried beneath the overwhelming brightness of foreground sources, such as our own galaxy. Separating this cosmic whisper from the noise requires sophisticated instrumentation, advanced data processing techniques, and innovative observational strategies. Despite these challenges, the potential rewards are immense. By uncovering the hidden history of the Dark Ages, we can gain insights into the processes that shaped the universe, from the formation of the first stars to the emergence of galaxies and the cosmic structures we see today. Imagine yourself deep in the Australian outback, a desolate expanse of red dust punctuated only by jagged rocks and resilient, desiccated shrubs. The oppressive heat of the day radiates through the arid air, offering no promise of rain, no respite from the sun's relentless glare. At first glance, the land appears lifeless, but subtle signs of life emerge as you walk. Sheep and cattle graze on sparse vegetation, adapting to a landscape that humans have long deemed too hostile to inhabit. These animals experience this world in ways alien to us, perceiving it through entirely different lenses, both literally and metaphorically. Humans are endowed with retinas that house color-sensitive cones tuned to red, green, and blue wavelengths of light. Yet the sheep and cattle roaming this rugged terrain lack the ability to see the red hues of the land altogether. The snake slithering past your feet is similarly blind to red, but it possesses a unique adaptation, the ability to sense infrared radiation, detecting the warmth of its surroundings. A scorpion scuttles into view, weaving through the sparse shrubs, its body fluorescing under ultraviolet light, an ability humans lack. These adaptations are a testament to the diverse ways life interacts with light. While humans are exceptional in their reliance on the optical spectrum, we have compensated by inventing technologies that extend our perception into ultraviolet, infrared, X-ray, and even radio wavelengths. Radio waves, the longest wavelengths of the electromagnetic spectrum, offer a unique portal into the universe. In our pursuit of long-distance communication, humans inadvertently stumbled upon the signals of celestial objects, birthing the field of radio astronomy. By creating technology capable of detecting these signals, we developed an entirely new kind of vision, a means to communicate not only across great terrestrial distances, but also with the distant past of the cosmos. Radio waves, imperceptible to the unaided eye, became a window into the hidden universe. As you journey further into the outback, you encounter an unexpected sight: strange metallic structures standing in stark contrast to the barren landscape. Some are shaped like bow ties, others resemble reflective tables, and a few evoke the spiky form of cacti. These peculiar constructions are not abstract art installations, but sophisticated scientific instruments. They serve as humanity's interface with the radio universe, a gateway to epochs long gone. Here, in one of the quietest places on Earth, lies the Murchison Radio Astronomy Observatory, a haven for detecting the faintest whispers of the cosmos. The Australian outback's isolation is a feature, not a flaw. Civilization tends to cluster around rivers and coastlines, leaving inhospitable regions like the outback sparsely populated. This emptiness is a boon for radio astronomers. Human activity, with its ubiquitous electronics, cell towers, and broadcast signals, creates interference that drowns out the delicate radio waves emanating from space. Deep in the Murchison Shire, covering 49,500 square kilometers, but home to just 100 people, radio astronomers have found a sanctuary. For over a decade, they have used this quietude to listen for echoes of the universe's dark ages. In 2018, one of these instruments detected a signal unlike any other. The telescope responsible, known as EDGE's experiment to detect the global epoch of reionization signature, is a deceptively simple device. Far from the imposing dish-shaped telescopes often associated with astronomy, EDGE's is a modest radio antenna. Its design resembles a TV or radio receiver, converting incoming radio waves into digital signals for analysis. Yet its mission is anything but ordinary. EDGES is finely tuned to detect the 21-centimeter line of neutral hydrogen, an emission that originated during the universe's earliest epochs, traveling to us across 13.7 billion years. The 21-centimeter line arises from a rare quantum phenomenon known as the hyperfine transition. Within neutral hydrogen atoms, the electron and proton can align or misalign their spins. When they transition between these states, they emit a photon with a precise wavelength of 21 centimeters. As the universe expands, these photons stretch or redshift, now arriving at wavelengths closer to 2 meters. By capturing these stretched photons, EDGES effectively measures the temperature of hydrogen gas across cosmic history, scanning photons emitted over hundreds of millions of years. At the start of the Dark Ages, the hydrogen gas was cool, coalescing around the dark matter web that served as the universe's scaffolding. As the first stars ignited, their radiation began to heat the surrounding hydrogen, imprinting subtle changes on the 21-centimeter signal. EDGES, perched silently in the remote outback, listened intently, its human operators thousands of miles away. By detecting variations in the signal's intensity and wavelength, EDGES unveiled a story billions of years in the making. The signal EDGES detected was both extraordinary and perplexing. It hinted at a universe colder than expected, challenging existing models of how the first stars influenced their surroundings. This discovery sparked debates and further investigations, highlighting the need for more sensitive instruments and innovative approaches. By observing at different wavelengths, the EDGES experiment delved deep into the cosmic dark ages, searching for the faintest signs of the first stars and the onset of the epoch of reionization. The challenge was monumental. The data gathered was cluttered with interference, the electronic imprints of the telescope itself, and the overwhelming radiation from our own galaxy. To uncover the faint whisper of ancient signals buried beneath this cacophony, the astronomers had to meticulously model and remove the noise, hoping to reveal a quiet murmur from the universe's earliest epochs. The CERES experiment, a radio antenna floating on an Indian lake, became the first to rigorously challenge the EDGES result. Despite employing advanced techniques and a pristine observational environment, CERES failed to detect the extreme signal reported by EDGES. Other teams followed suit, finding no evidence to support the unexpected cooling. Gradually, the scientific community began to restore confidence in the original cosmological models, shelving the exotic hypotheses, at least for now. Nevertheless, the quest to understand the cosmic dark ages and pinpoint the birth of the first stars remains far from over. While EDGES faced challenges and controversy, it succeeded in highlighting the immense difficulty of detecting the faint signals from this era. The cosmic dark ages signal is hundreds to thousands of times fainter than the radiation from our galaxy, making this one of the most demanding experiments in astronomy. In the same remote Australian outback where EDGES conducted its observations, the Murchison Wide Field Array continues to scan the skies. Using its distinctive bow-tie antennas, known locally as the ear that listens to the sky, it searches for the telltale bubbles of ionized hydrogen that mark the epoch of reionization. These efforts are soon to be joined by the Square Kilometre Array, SKA, the most ambitious radio astronomy project ever conceived. When complete, the SKA will comprise 130,000 antennas spread across the Murchison Desert, creating a telescope so sensitive it could detect the faint radar signals of an airport on a planet 10 light-years away. The SKA promises to peer back across the first billion years of cosmic history, illuminating the Dark Ages and the Epoch of reionization in unprecedented detail. Yet even in this remote location, human activity and atmospheric interference impose limits. Mobile phones, radio broadcasts, and satellites all contribute noise that obscures the faint signals from the early universe. To push beyond these constraints, scientists are looking to the ultimate quiet zone, the far side of the moon. Shielded by the moon's bulk, a radio telescope placed in this environment would be free from terrestrial interference, providing an unparalleled vantage point for studying the cosmic dark ages. Preparatory tests are already underway to pave the way for this next-generation observatory. The cosmic dark ages lasted for nearly 200 million years, but they were only dark to our eyes. To the metal antennas of radio telescopes, the universe was bright with 21-centimeter photons, tracing the distribution of hydrogen gas as it coalesced around the dark matter web. This hidden activity laid the groundwork for the universe as we know it. The emergence of the first stars marked a turning point, their light piercing the darkness and transforming the cosmos. Stars gathered into galaxies, which in turn created the luminous structures that define the universe today. The end of the cosmic dark ages was not a sudden event, but a gradual awakening, as light spread across the cosmos and reshaped its very fabric. Through ongoing efforts and ever more advanced technology, humanity edges closer to unveiling the secrets of this transformative epoch. Each discovery is a step toward illuminating the quiet, industrious beginnings of the universe, a time when the seeds of all we see today were sown. The journey to uncover this story continues, driven by our unrelenting desire to understand the cosmos in all its hidden brilliance. Where are we heading in this vast cosmic ocean? What unseen forces chart the course of entire galaxies, and what mysteries lie hidden beyond the stars? Is our journey through space a mere drift, or is it guided by something far greater, an irresistible pull toward the unknown? In the infinite expanse of the cosmos, nothing stands still. Every star, every planet, every galaxy is caught in a perpetual motion, bound by the gravitational currents of the universe. Yet, amidst this endless dance, there is something peculiar about the movement of our Milky Way galaxy. Astronomers in the 1970s made a discovery that would challenge our understanding of the cosmos and ignite decades of investigation. The Milky Way, it seemed, was not just orbiting within its own cluster of stars. It was moving, and not just moving, hurtling along with countless neighboring galaxies toward a specific point in space. But this was no ordinary destination. Hidden behind a thick veil of gas and dust known as the zone of avoidance, it remained unseen, a mystery cloaked in darkness. It was as if the Milky Way, like a small raft adrift in a vast ocean, had been caught in a powerful current, drawn toward an unseen force of staggering proportions. Two astronomers, R. Brent Tully and J. Richard Fisher, sought to unravel this enigma. Using the Parkes radio telescope in Australia, they mapped the motions of distant galaxies. The patterns they found were striking. These galaxies all seemed to be heading toward the same general region of space. Around the same time, other researchers were studying the cosmic microwave background, the faint afterglow of the Big Bang. By analyzing its temperature variations, they uncovered another clue, a subtle imbalance in its warmth across the sky. This imbalance wasn't random. After accounting for the motion of the sun around the center of the Milky Way, a residue remained, an additional velocity of hundreds of kilometers per second. It was as though our galaxy and the galaxies around it were being tugged by a vast gravitational force, one that could stretch across tens of millions of light years. The only problem? We couldn't see it. It lay buried behind the zone of avoidance, an invisible beacon pulling us closer with every passing moment. Astronomers gave it a name as enigmatic as the force itself, the Great Attractor. It was a fitting title for something so powerful, so mysterious. This singular point in the cosmos seemed to pull not just the Milky Way, but entire clusters of galaxies containing hundreds of billions of stars into its gravitational embrace. It was a cosmic sink of gravity, a point where the ordinary rules of motion no longer seemed to apply. And yet, as strange as this may sound, this is far from unusual in the universe. The cosmos is a dynamic, restless place. Our Earth orbits the Sun orbits the Milky Way's core, and the Milky Way itself is just one part of a larger cosmic web. Everything is moving, and everything is being pulled by something greater. The Great Attractor is no exception. It is part of a grander cosmic flow. Over the years, astronomers discovered that this mysterious force is merely the tip of an iceberg, a vast structure of unimaginable scale. It is connected to even larger patterns of motion, including the Laniakea supercluster, an enormous web of galaxies that spans over 500 million light-years. This revelation raised even more questions. What is the Great Attractor? Is it the remnant of a colossal black hole, a dense region of dark matter, or perhaps something even stranger, a feature of the universe we have yet to comprehend? For now, the answers remain elusive, hidden behind the veil of interstellar dust and the limits of our technology. But the search continues. Astronomers are developing more powerful instruments capable of peering through the zone of avoidance and mapping the unseen structures of the universe. They hope to uncover the true nature of the Great Attractor and the forces driving this cosmic flow. What they find may reshape our understanding of gravity, dark matter, and the very fabric of space-time. As we gaze into the cosmos, we are reminded that we are part of something much larger than ourselves. Our galaxy, our solar system, our planet, all are participants in this grand celestial journey. We are moving, together with countless stars and galaxies, drawn by forces we cannot yet fully explain. And so the question lingers, where are we going? What lies at the heart of this gravitational mystery? And will we ever truly understand the forces that guide us through the universe? Where are you going? Motion defines the universe. It is the thread that weaves the fabric of our existence, shaping everything from the smallest particles to the largest cosmic structures. Science, in many ways, is the story of our growing awareness of this cosmic restlessness. For millennia, the brightest minds in Europe and the Middle East believed the Earth was a stationary center of the universe, with the heavens revolving around it. Early astronomers worked tirelessly to explain and predict the motion of celestial objects, the sun, the moon, planets, and stars. Their models, intricate and complex, managed to describe these movements with surprising accuracy. Yet, beneath this success lay an unwieldy system, filled with nested circular orbits and countless mathematical adjustments. In 1543, on his deathbed, Polish astronomer Nicholas Copernicus published On the Revolutions of the Heavenly Spheres. This work proposed a radical restructuring of the cosmos. In Copernicus's universe, the sun stood at the center, still and immovable, while the Earth and the other planets orbited it. This heliocentric model promised a more elegant explanation of celestial motions, but left lingering questions. If the Earth moved, why couldn't we feel it? Where was the great rush of wind? Why weren't we flung into space by the Earth's incredible rotation? It took centuries of scientific progress, culminating in Isaac Newton's theory of gravity, to address these questions. Today, we understand that we do not feel Earth's motion because we are part of it, moving together with our planet through the vacuum of space. Without an atmosphere to push against, our motion remains imperceptible to our senses. But this realization posed another challenge. How could we be certain that the Earth truly moved? What was the standard frame of reference? Newton assumed the existence of a universal frame of reference, an absolute ruler against which all motion could be measured. However, Einstein's theory of relativity overturned this idea. In Einstein's universe, there is no absolute reference point. Motion is always relative, measurable only in relation to another object. This principle gave rise to the fabric of space-time, the equivalence of mass and energy, and the immutable speed of light. Imagine drifting in a rocket through the void, encountering a friend in another unpowered ship. Both of you are moving at constant speeds, each claiming to be at rest while the other moves. Relativity tells us that both perspectives are equally valid. Even so, we can infer the Earth's rotation from phenomena like the Coriolis force, which shapes weather patterns into spiraling hurricanes. Without stars to guide us, we could still deduce Earth's spin by observing its effects on the physical world. However, understanding Earth's motion within the larger universe requires more. We need a cosmic yardstick, something to measure against. Thankfully, the universe's expansion provides just that. The cosmos is not static, but stretches over time, its galaxies drifting apart like ink dots on an inflating balloon. This expansion gives us a preferred frame of reference, a universal flow against which deviations can be measured. These peculiar velocities, distinct from the general outward motion, help us understand not only Earth's place, but also the intricate dance of galaxies. On Earth's surface, motion is staggering. Depending on your location, you may be spinning at up to 1,600 kilometers per hour due to Earth's rotation. Over an average lifetime of 80 years, this adds up to 1 billion kilometers. But this is only the beginning. The Earth orbits the Sun at an average speed of 30 kilometers per second, traveling an astonishing 80 billion kilometers in a human lifetime. These orbits, though immense, are circular journeys that lead back to the same point. We're moving, but not really going anywhere. Yet our solar system, carried by the Sun, is also in motion within the Milky Way. Orbiting the galactic center at an average speed of 230 kilometers per second, it takes 230 million years to complete one revolution. This incredible speed provides compelling evidence for the existence of dark matter. The visible matter in the Milky Way, stars, gas, and dust, is insufficient to account for the gravitational forces holding the galaxy together. Without dark matter's unseen mass, the Sun's velocity would have ejected it from the Milky Way billions of years ago. Beyond its orbit, the Sun oscillates through the galactic plane like a buoy bobbing on a dark sea. Influenced by the gravity of neighboring stars, it rises and falls thousands of light years over millions of years. At present, the Sun is plunging through the local bubble, a vast low-density cavity in the interstellar medium created by ancient supernova explosions. This journey through the bubble, which spans about 1,000 light-years, will continue for several million more years. And yet, this too is part of a larger story. The Milky Way itself is in motion, heading toward our nearest galactic neighbor, Andromeda. These two galaxies, drawn together by mutual gravitational attraction, will collide in roughly 4.5 billion years, merging to form a new galactic structure. This cosmic ballet is a testament to the universe's restless dynamism. But even this colossal interaction is not the final word. The Milky Way, along with Andromeda and other members of the local group, is being pulled toward a region of immense gravitational influence known as the Great Attractor. This mysterious force, obscured by the dense gas and dust of the zone of avoidance, tugs on entire clusters of galaxies. The Great Attractor is itself part of an even larger structure, the Laniakea supercluster, a vast network of galaxies spanning over 500 million light-years. Billions of years from now, the night sky will be unrecognizable. The moon will have drifted farther from Earth, appearing smaller and fainter. The Sun, swelling as it exhausts its nuclear fuel, will burn larger and brighter. Familiar constellations will dissolve, replaced by new stellar arrangements formed by stars from our shifting solar neighborhood. Amid these changes, one celestial object will dominate the heavens, the Andromeda Galaxy, transformed into a breathtaking and ever-changing spectacle. Today, Andromeda occupies a modest portion of the sky, about the size of a fist held at arm's length. But as the millennia pass, Andromeda will loom ever larger, growing to fill the night sky. Its shape, once an elegant spiral, will become twisted and distorted under the influence of the immense gravitational forces binding it to the Milky Way. This cosmic entanglement will unfold over billions of years, culminating in a majestic and cataclysmic merger. The story of Andromeda's motion begins in the 1920s with Edwin Hubble's revelation that the Andromeda Nebula was not part of the Milky Way, but an entire galaxy unto itself, situated an astonishing 2.5 million light-years away. This discovery expanded humanity's view of the universe and established Andromeda as our closest galactic neighbor. Measuring its motion, however, proved to be a complex challenge. In 1957, Dutch astronomer Hendrik van de Hulst made a breakthrough using radio astronomy. By studying the faint 21 centimeters radiation emitted by neutral hydrogen in Andromeda, he mapped its movement. The results revealed a blue shift, a shortening of wavelengths, indicating Andromeda was moving toward us at an average speed of 296 kilometers per second. After accounting for the Sun's motion around the galactic center, the net motion of Andromeda toward the Milky Way was calculated at approximately 100 kilometers per second. This motion, however, is not unidirectional. In the context of the universe's expansion, both galaxies are moving toward a shared gravitational center, bound by their mutual attraction. It wasn't until 2012, when astronomers using the Hubble Space Telescope measured Andromeda's lateral motion that we confirmed a direct collision course. The cosmic ballet between the Milky Way and Andromeda will begin in earnest about 2 billion years from now. As the galaxies draw closer, gravitational forces will stretch and distort them, creating phenomena that echo familiar tidal interactions on Earth. The parts of each galaxy nearest to the other will experience stronger gravitational pulls, while distant regions will feel weaker forces. These tidal interactions will elongate the galaxies, pulling entire spiral arms apart and forming immense tidal tails composed of stars and gas. This gravitational interplay will also spark intense bursts of star formation. Gas clouds compressed during the merger will collapse, igniting furious rounds of stellar birth at rates thousands of times higher than today. Bright, massive stars will dominate this new generation, their light and energy creating a dazzling display across the merged galaxies. Over time, bridges of stars and gas will form between the two galaxies, linking them as they spiral toward their eventual union. The collision of Andromeda and the Milky Way will not be a sudden, catastrophic event. Galaxies are composed mostly of empty space. Their stars are so far apart that direct collisions between them will be rare. Instead, the gravitational interactions will disrupt the orbits of stars, reshaping the flat disks of the galaxies into a chaotic, overlapping mass. Some stars will be ejected entirely, flung into intergalactic space by the immense forces at play. Others will settle into new orbits within the merged galaxy. The first pass of the galaxies will take over 100 million years, followed by a series of collisions and separations over the course of several hundred million years. Each encounter will compress gas clouds, triggering fresh waves of star formation. The final stages of the merger, occurring around 5 billion years from now, will see the Milky Way and Andromeda coalesce into a single, unified structure. Astronomers predict the resulting galaxy, often dubbed Milkomeda, will be a massive elliptical galaxy, marked by a dense central core and a smooth, featureless halo of stars. The brief era of intense star formation will eventually end as the galaxy's gas reserves are depleted. The young hot stars will burn out quickly, leaving behind long-lived dim red dwarf stars. Milkomeda will fade into a quiet red-hued existence, its days of stellar brilliance behind it. The merger will also leave an imprint on the surrounding environment. Streams of stars and gas, remnants of tidal interactions, will extend far beyond the boundaries of the new galaxy. These structures, known as stellar streams, will serve as evidence of the cosmic drama that unfolded billions of years earlier. Beyond the Great Attractor, a cosmic odyssey. Mathematics often serves as a crystal ball, offering insights into the distant realms of space and time. This narrative begins not in the laboratories of modern cosmology, but in an unexpected historical setting, revolutionary France. In 1792, Gaspard Monge, a French mathematician and minister of the Marine, sought solutions to logistical problems, aiming to optimize the transport of goods. Unbeknownst to him, his foundational work would ripple through centuries and disciplines, eventually contributing to our understanding of the universe's grand architecture. Decades later, André-Marie Ampère, celebrated for his work in electromagnetism, extended Monge's principles, crafting equations applicable to economic models, optimizing the allocation of resources between mines and factories. The practical utility of these equations found renewed purpose during World War II, when Soviet mathematician Leonid Kantorovich adapted and advanced Monge's and Ampère's methods to solve the Soviet Union's complex logistical challenges. However, it was in the 1970s that Canadian-American cosmologist Jim Peebles identified a far-reaching application of these mathematical tools, deciphering the mechanics of galaxy formation. Building on Peebles' insights, French astronomer Roya Mohaye and Russian astrophysicist Andrei Sobolevsky wielded the Monge-Ampère-Kantorovich equations as a cosmological crystal ball. They ingeniously reconstructed the past trajectories of galaxies by analyzing their current positions and velocities. Galaxies move under the influence of mutual gravitational attraction, and by leveraging our understanding of gravitational laws, the equations enabled a method to transport galaxies back in time. Although each step introduces increasing uncertainties, this technique offers a window into the cosmic past, mapping galaxies' journeys billions of years ago. Brent Tully and collaborators have since developed cosmic flows, a series of continuously updated catalogs charting tens of thousands of galaxies' motions. These maps not only illuminate the past, but also predict the future trajectories of galaxies, including the Milky Way. Through these efforts, scientists have unraveled the mysteries surrounding the Great Attractor, a gravitational anomaly influencing the motion of our galaxy and its neighbors. The universe's expansion provides a preferred frame of reference against which all motion can be measured. The cosmic microwave background, CMB radiation, a relic of the universe's infancy when it transitioned from a plasma state to a neutral gas, roughly 380,000 years after the Big Bang, serves as this benchmark. The CMB's near-perfect uniformity, with temperature deviations of only 1 part in a million, captures the universe's primordial homogeneity. Observing the CMB reveals a subtle dipole pattern, a slight blue shift in the direction of the constellation Leo, and a corresponding redshift toward Aquarius. This discrepancy stems from our motion relative to the CMB. The measured shift implies a velocity of approximately 600 kilometers per second. After accounting for the Sun's orbit around the Milky Way and the Milky Way's impending collision with the Andromeda galaxy, a residual velocity of about 300 kilometers per second remains, pointing directly toward the Great Attractor. The universe assembles itself through hierarchical structure formation, beginning with galaxies. The Milky Way, born as a modest collection of stars, grew through successive mergers, a process mirrored across the cosmos. Groups of galaxies, such as the local group containing the Milky Way, Andromeda, Triangulum, and several dwarf galaxies, are gravitationally bound systems that continue to coalesce. Within 100 billion years, these groups will merge into a single mega-galaxy. Clusters of galaxies represent the next tier of this hierarchy. The Virgo cluster, the nearest major cluster, exerts a powerful gravitational pull on the local group. Over billions of years, this gentle tug has transformed into a formidable force, drawing galaxies inexorably inward. Yet, clusters are not the universe's largest structures. They themselves are components of superclusters, vast, loosely defined aggregations of clusters. In 2014, Brent Tully and collaborators redefined superclusters using the Monge-Ampere-Kantorovich framework. By mapping galaxies' motions, they revealed that the so-called Virgo supercluster is but a single branch of a far grander entity, Laniakea. Spanning over 500 million light-years and containing 100,000 galaxies, Laniakea's name, meaning immense heaven in Hawaiian, reflects its vastness and beauty. The local group belongs to the Virgo branch, which in turn is part of Laniakea. All are drawn toward a singular destination, the Great Attractor. The Great Attractor's influence emerges from billions of years of cosmic evolution. Situated at the heart of Laniakea, it represents the culmination of gravitational interactions across unimaginable scales. While its exact nature remains shrouded due to its location in the zone of avoidance, a region obscured by the Milky Way's dense disk, observations suggest it is part of a massive cluster or supercluster complex. The Great Attractor epitomizes the dynamic nature of the universe. Galaxies, clusters, and superclusters are not static structures, but living entities shaped by ceaseless motion and interaction. This intricate dance, governed by gravity, began in the universe's earliest moments and will continue for billions of years to come. Our understanding of the Great Attractor remains veiled, obscured by the so-called zone of avoidance, a region of the sky rendered inaccessible to visible light telescopes by the dense dust of our own galaxy. Yet certain wavelengths, radio, infrared, and X-ray, possess the ability to pierce through this cosmic shroud. With these tools, astronomers have managed to glean glimpses of what lies beyond, revealing fragments of the vast structures within the Great Attractor's domain. At the heart of Laniakea, the immense supercluster housing the Milky Way and approximately 100,000 other galaxies, lies the Norma cluster. Named for the constellation through which it is observed, the Norma cluster sits roughly 220 million light-years away. This massive structure, several times larger than an average galaxy cluster, forms the focal point of our galactic migration. Despite traveling at speeds exceeding 100 kilometers per second, it would take the Milky Way more than 100 billion years to reach Norma's gravitational embrace. Like all galaxy clusters, Norma's formation is the product of countless mergers and the inexorable pull of gravity. Uniquely, it occupies the bottom of a colossal gravitational well, serving as the central attractor for this region of the universe. Over time, Norma will continue to grow, gathering material as its influence deepens. Yet, even as it looms large in our understanding, recent surveys employing advanced techniques, notably the Monge-Ampere-Kantorovich reconstruction, indicate that Norma's role is not the final chapter in this story. While the Norma cluster dominates locally, its gravitational pull falls short of accounting for the observed velocities of galaxies within Laniakea. This suggests the existence of an even larger structure, deeper in space, the Shapley supercluster. Discovered in the 1930s by Harlow Shapley, this massive entity lies over 650 million light-years away. As one of the universe's largest known superclusters, Shapley exerts its gravitational influence across hundreds of millions of light-years, dwarfing the scale of Laniakea. The Shapley supercluster's incredible mass hints at its significance as the next major destination in the cosmic flow. If the universe's vast movements continue unabated, Laniakea itself will ultimately collapse into a single massive structure, a supersized Norma cluster, which would, in turn, converge with Shapley's heart. The gravitational ballet between these immense entities underscores the layered complexity of cosmic evolution. The narrative of motion extends beyond these superclusters. In 2008, NASA astronomer Alexander Kashlinsky identified a peculiar phenomenon using data from the cosmic microwave background, CMB. Known as the kinematic Sunyaev-Zeldovich effect, this signal arises when CMB photons interact with the hot gas within galaxy clusters. Kashlinsky's analysis revealed a large-scale movement of clusters toward a point between the constellations Centaurus and Vela, a phenomenon he dubbed dark flow. This flow, with velocities ranging between 600 and 1,000 kilometers per second, encompasses vast portions of the observable universe. However, the mystery of dark flow deepens when considered against current cosmological models. The observed density variations in the universe appear insufficient to generate such coherent large-scale motion. While the ESA's Planck satellite later cast doubt on dark flow's existence, the debate persists, emblematic of the enduring enigmas that define the cosmos. The forces shaping the universe are not solely contemporary. Imprints from its earliest moments continue to resonate, influencing the large-scale structure we observe today. When the universe was in its infancy, a hot, dense plasma, sound waves known as Berionic acoustic oscillations propagated through the medium. As the universe expanded and cooled, these waves froze in place, leaving behind faint imprints in the distribution of matter. Recent surveys have uncovered these echoes, most notably a vast, shell-like structure named Ho'olelana. With a radius exceeding 400 million light-years, this formation encompasses features like the Sloan Great Wall and the Boats supercluster. Brent Tully and collaborators, who identified this structure in 2023, suggest it represents a single baryonic acoustic oscillation, a remnant of the primordial universe's chaotic symphony. The Hawaiian name Ho'olelana, meaning murmurs of awakening, poetically captures the essence of this ancient relic. Gravity's role in the universe is complemented by an opposing force, repulsion. Among the most intriguing manifestations of this phenomenon is the dipole repeller, a vast void located opposite the Shapley supercluster. Unlike dense regions, which pull matter inward, voids like the dipole repeller exert a pushing influence, propelling galaxies away from their periphery. This counterintuitive behavior is driven by the void's content, dark energy, which dominates its vast expanse. The dipole repeller's influence adds a new dimension to our understanding of cosmic motion. It suggests that the universe's structure is shaped not only by gravitational attraction, but also by the interplay of repulsive forces. Over time, these dynamics will unravel the cosmic web, preventing galaxies from converging at focal points like the Great Attractor. Instead, the universe will become increasingly diffuse, its grand structures dissolving under the inexorable influence of dark energy. The story of the Great Attractor and its neighboring structures is one of perpetual motion, a symphony conducted by the twin forces of gravity and dark energy. From the veiled depths of the zone of avoidance to the vast reaches of the Shapley supercluster, the cosmos reveals itself as a dynamic, interconnected tapestry. As we unravel these mysteries, we find ourselves not only mapping the universe, but also engaging with its profound narrative, one of creation, movement, and eventual dispersion. The unfolding cosmos, Einstein, dark energy, and the fate of the universe. In the annals of scientific history, there are few figures as towering as Albert Einstein. His intellect, often described as transcendent, propelled him to make groundbreaking discoveries that transformed our understanding of the physical universe. Yet, even a mind of his caliber was not immune to doubt and missteps. Among his many triumphs, there exists a curious detour, a mathematical addition born not from discovery, but from the weight of contemporary assumptions. This addition, famously called Einstein's greatest blunder, would later re-emerge as a pivotal element in our understanding of the universe's accelerating expansion. In 1915, Einstein unveiled his masterpiece, the general theory of relativity, a framework that redefined gravity not as a force, but as the curvature of space-time itself. With equations so elegant they seemed inevitable, Einstein provided a toolset capable of describing phenomena from the motion of planets to the bending of light by massive objects. Inspired by this success, he sought to apply his equations to the grandest scale imaginable, the entire universe. At the time, prevailing wisdom held that the cosmos was static and unchanging, a serene expanse where galaxies and stars might move locally but remained collectively at rest. When Einstein plugged the mathematics of general relativity into this cosmological picture, he encountered a perplexing result. The equations resisted stasis. They demanded dynamism. They suggested a universe that was either contracting under its own gravity or expanding outward in an unrelenting sprawl. For Einstein, this conclusion was unsettling. A dynamic universe clashed with the philosophical and scientific conventions of his era, and he hesitated to challenge such entrenched beliefs. In the 1920s, Edwin Hubble's observations of distant galaxies revealed that they were moving away from us. Moreover, the farther a galaxy was, the faster it receded, a relationship now encapsulated in Hubble's law. The universe was not static, it was expanding. The cosmological constant, introduced to maintain stasis, was rendered unnecessary. Einstein, recognizing his error, reportedly called Lal his greatest blunder. The term faded from prominence, relegated to a historical footnote. Yet the story of the cosmological constant was far from over. Decades later, theoretical physicists revisited Lal in light of advances in quantum mechanics. The vacuum of space, once thought of as empty, was revealed to be anything but. Quantum fluctuations filled the vacuum with a seething energy, a vacuum energy that imbued even the emptiest reaches of space with a subtle but pervasive influence. Remarkably, this vacuum energy was mathematically equivalent to Einstein's cosmological constant. Though discarded by Einstein himself, Lal had found new theoretical footing. The true vindication of the cosmological constant came in 1998, when two independent teams of astronomers announced a startling discovery. The expansion of the universe was not slowing down, as might be expected from gravitational attraction, but accelerating. This acceleration, observed through the dimming light of distant supernovae, pointed to the presence of a mysterious force, dubbed dark energy, that counteracted gravity on cosmic scales. The most plausible explanation for dark energy was the vacuum energy of spacetime, a concept eerily reminiscent of Einstein's long-abandoned Enlil. Today, dark energy accounts for roughly 70% of the universe's total energy content. It dominates the cosmos, shaping its destiny in profound and unsettling ways. To understand this influence, we must trace the cosmic timeline. For billions of years after the Big Bang, the universe was governed by matter and radiation. Gravity, stemming from the clumping of matter, acted as the principal architect of cosmic structures. Galaxies formed, clustered into groups and coalesced into vast superclusters like Laniakea, our local region of the cosmic web. But as the universe expanded, its matter grew increasingly diluted. Around 5 billion years ago, the density of matter fell below that of dark energy. This moment marked a profound shift, the era of dark energy dominance. Dark energy, tied to the fabric of space-time itself, behaves differently from matter. While matter disperses as the universe expands, dark energy appears to increase, filling the growing void with ever more intensity. This feedback loop drives the accelerated expansion, stretching the cosmos at an ever faster rate. As a result, regions of the universe are being torn apart. Galaxies that are not gravitationally bound to one another are receding faster than the speed of light, effectively disappearing from view. The cosmic web, once an interconnected tapestry of galaxies and filaments, is unraveling. The voids, vast, empty regions of space, are the front lines of this cosmic deconstruction. Filled with little more than dark energy, these regions expand at an accelerated pace, driving the galaxies at their boundaries farther apart. Over time, the voids will merge, leaving behind isolated islands of gravitationally bound structures. Our local group, containing the Milky Way, Andromeda, and a few dozen smaller galaxies, will endure. Over billions of years, these galaxies will merge into a single elliptical galaxy, a solitary beacon in an otherwise dark and empty universe. Clusters like Virgo, dense with thousands of galaxies, will also survive, but the larger superclusters, including Laniakea, are doomed. They lack the cohesion to resist the relentless pull of dark energy. The ultimate fate of the universe hinges on the nature of dark energy, a mystery we have yet to unravel. If dark energy remains constant, the cosmos will continue to expand forever, growing colder and darker as galaxies exhaust their fuel and stars wink out. This is the heat-death scenario, where entropy reaches its maximum and no useful energy remains. If, however, dark energy increases in strength, the universe faces an even more dramatic end, the Big Rip, in which the accelerated expansion tears apart galaxies, stars, planets, and even atoms. Whatever the outcome, dark energy ensures that the universe will not rest. It is the force driving the cosmos into an ever-expanding future, a relentless agent of change born from the vacuum itself. Einstein's cosmological constant, once a tool to preserve stasis, now serves as a reminder of the dynamic and ever-evolving nature of the universe. As we gaze into the depths of space, we are not merely witnessing distant galaxies, we are observing the forces that will shape the ultimate destiny of all that exists. The future trajectory of the Milky Way is intertwined with that of the local group, bound on a seemingly inevitable collision course with the Andromeda galaxy. This cosmic dance, though dramatic, offers little solace against the inexorable pull of larger forces that shape the universe. Even as we chart this impending merger, the local group's fate appears to be one of isolation, unable to reach the gravitational sanctuary of the Virgo cluster or the enigmatic Great Attractor. Instead, the local group will succumb to the accelerated expansion of the universe, a consequence of dark energy's relentless influence. Distant galaxies and clusters will dim, their light fading as they cross the cosmological horizon, beyond which they are forever lost. Hundreds of billions of years from now, the local group will have coalesced into a singular mega-galaxy, adrift in an expanding void. Over the course of trillions of years, this solitary island of matter will fragment further. Gravitational interactions will eject stars, one by one, into the abyss. Once these stars escape the gravitational clutches of the megagalaxy, they too will succumb to the accelerated expansion, as if erased from existence. Gradually, the galaxy will dissipate, leaving behind an ever-dwindling remnant. This fate is not unique to galaxies, but applies universally. Over hundreds of trillions of years, every macroscopic object, from stellar remnants to planetary husks, will be cast adrift. The accelerated expansion of the universe ensures that these objects will become utterly isolated, separated by vast distances that grow faster than light itself can traverse. The faint glow of the cosmic microwave background will remain as a spectral echo of a universe once teeming with complexity. In this vast and empty expanse, the the universe will approach a state of rest, its dynamics stilled by the unyielding hand of dark energy. On smaller scales, the interplay between quantum mechanics and information reveals another realm of inaccessible knowledge. Einstein, in his debates with Bohr, sought to challenge the fundamental indeterminacy of the quantum world, proposing thought experiments to argue that the uncertainty principle was an artifact of incomplete understanding. Yet, Bohr's meticulous rebuttals highlighted the inherent limitations of quantum mechanics and affirmed the principle's validity. Einstein reluctantly conceded the probabilistic nature of quantum phenomena, but maintained that quantum mechanics was an incomplete description of reality. At the heart of this indeterminacy lies the Schrödinger equation, which governs the evolution of quantum systems. Unlike classical physics, where the future behavior of a system can be determined precisely from its initial conditions, quantum mechanics offers only probabilities. Every particle is associated with a wave function, a mathematical description of its likelihood of being found in a particular state. The wave's peaks and troughs indicate regions of high and low probability, but they provide no definitive answers, only possibilities. Remarkably, quantum uncertainty extends beyond the subatomic realm. In 2019, researchers led by Jakob Fine at the University of Vienna demonstrated the wave-like nature of a molecule composed of 2,000 atoms. This groundbreaking experiment revealed that the quantum fuzziness, once thought confined to the microscopic domain, could manifest at surprisingly large scales, challenging our intuitions about the boundaries of quantum behavior. Beyond the reach of quantum experiments lies another inaccessible domain: black holes. These enigmatic objects, the densest repositories of information in the universe, are shrouded in mystery. A black hole's defining feature is its event horizon, an invisible boundary beyond which nothing, not even light, can escape. The contents of a black hole, the remnants of the stars it consumed, and any additional material it accumulated over time, are irretrievably hidden from the outside universe. While it is theoretically possible to access this information by crossing the event horizon, such an endeavor comes at a fatal cost. Within a finite amount of time, as measured by an observer's wristwatch, the traveler would reach the singularity, where the laws of physics break down, and any revelations gained would be lost forever. The information paradox posed by black holes underscores the limits of our knowledge. To an external observer, a black hole reveals only its mass, angular momentum, and charge. Everything else, the intricate details of its formation and history, is veiled in darkness. Similarly, the past itself represents an inaccessible repository of knowledge. While the present state of the universe reflects its history, the exact details of past events are irretrievable, accessible only through imperfect memories and surviving artifacts. As we confront these barriers to understanding, we are reminded of the finite bounds of accessible knowledge in the universe. The observable cosmos contains somewhere between 500 billion and 2 trillion galaxies, each hosting billions to trillions of stars. Even if we could instantaneously catalog every galaxy and star, this dataset would represent the entirety of information available to address questions about galactic and stellar evolution. Beyond these galaxies lies a vast ocean of particles and fields. The observable universe is estimated to contain 10 to the power of 80 protons, along with comparable numbers of electrons, neutrinos, and dark matter particles. Photons, primarily from the cosmic microwave background, number around 10 to the power of 90. Each of these particles carries information about the universe, but even their complete measurement would not exhaust the limits of accessible knowledge. To fully comprehend the universe, we must delve deeper, probing the quantum fields that underpin reality. These fields exist as vibrations in space-time and give rise to particles as localized excitations. At the smallest scales, these fields exhibit quantum fluctuations, a phenomenon known as quantum foam. The quantum foam represents the fundamental granularity of space-time, where energy briefly manifests as particle-antiparticle pairs before annihilating. This seething turbulence is most pronounced at the Planck length, approximately 1.61 times 10 to the power of negative 35 meters, where the smooth fabric of spacetime gives way to chaotic dynamics. The Planck length serves as the ultimate resolution limit to knowledge, a boundary beyond which our understanding falters. By dividing the observable universe into Planck scale units, we can estimate its total information content. Advanced theories, including those inspired by Claude Shannon's work on entropy and information, suggest that each Planck scale unit corresponds to a single bit of information. This approach yields a staggering estimate. The universe contains approximately 10 to the power of 120 bits of information. Despite this immense wealth of data, the universe imposes insurmountable limits on what can be known. Even if we were to achieve complete knowledge of the observable universe, questions would remain unanswered, constrained by the finite scope of accessible information. As we push the boundaries of exploration from the vast expanses of cosmic structure to the intricate workings of quantum systems, we are confronted with the profound realization that the universe's mysteries are not infinite, but bounded. Yet, within these boundaries lies a universe of extraordinary depth and beauty, a testament to the power of human curiosity and imagination. In contemplating the ultimate limits of knowledge, we are drawn to wonder. Even if we could measure every particle, decode every quantum fluctuation, and chart the evolution of every galaxy, would we truly grasp the essence of the universe? Or would the act of understanding itself transform, revealing new perspectives and possibilities beyond the reach of our current imagination? The journey to answer these questions is as boundless as the universe itself, a testament to the enduring quest for knowledge that defines our place within the cosmos. The limits of infinity. When first introduced, the idea of true limits, of boundaries to infinity, was met with fear and resistance. For generations, it was dismissed, ridiculed, and even suppressed, viewed as heretical to the deeply ingrained convictions of a flourishing civilization. To entertain such an idea was to question the very foundation of their worldview, the boundless potential of exploration, knowledge, and mastery of the cosmos. Yet, as millennia passed, and no alternative path to ultimate understanding presented itself, the idea began to gnaw at the collective psyche of the civilization. What if their grasp on the universe was not incomplete because of insufficient effort or technology, but because the universe itself imposed insurmountable barriers to knowledge? By this time, the civilization was ancient, transcending the imagination of even their most optimistic ancestors. They had long abandoned the constraints of planetary existence, spreading their influence across the vast expanse of their home galaxy. Having encountered no other intelligent life, they reshaped their galaxy to their will, harnessing its energy, manipulating its matter, and achieving the once unimaginable status of a Kardashev Type 3 civilization, a society capable of wielding the energy of an entire galaxy. Yet even as they achieved unparalleled dominion, their progress began to falter. They found themselves constrained by limits they could not surmount. Their machines, built to think beyond human capacity, mirrored their creators too closely, and their insights were bound by the same frameworks and biases. Despite their technological triumphs, they remained tethered to their origins, their perspective shaped by the genetic and cultural heritage of their ancient past. Desperation gave rise to a radical plan to seed intelligence anew, untainted by their history, on a distant, unremarkable world. This world was chosen carefully. It orbited a stable star, was rich in the essential ingredients for life, and held the potential for biological complexity. The civilization intervened subtly, modifying the primordial conditions to encourage the emergence of life and, eventually, sapience. Encoded within the chemical precursors of life were deliberate tweaks, imperceptible but profound, to guide evolution toward consciousness. The architects of this project did not seek to control the outcome. They yearned for novelty. They slumbered through the eons, dreaming of the insights that might one day arise from this experiment, insights they hoped would break through their own limitations. The story of this civilization invites reflection on the boundaries of knowledge. Despite the monumental achievements of science, technology, and philosophy, there remain questions that defy comprehension. Even as humans, we grapple with profound mysteries: the nature of time, the origin of consciousness, the essence of existence itself. Science, for all its power and adaptability, may not be the ultimate tool for uncovering every truth. Indeed, before the scientific method emerged, knowledge was pursued through philosophy, mathematics, and introspection, approaches that continue to enrich our understanding of the universe. Consider mathematics, a domain where abstract truths are derived independently of the physical world. Mathematical axioms, once proven, remain true whether or not they have practical application. Similarly, philosophical traditions like skepticism probe the very foundations of knowledge, questioning whether we truly understand the universe or merely construct convenient illusions. Even within the physical sciences, there are limits to what we can know. Take the quantum realm, where uncertainty is a fundamental feature. The Heisenberg uncertainty principle dictates that we cannot simultaneously know both the position and momentum of a particle with infinite precision. This limitation is not a shortcoming of our tools or methods, but an intrinsic property of reality itself. On cosmic scales, the horizon of the observable universe imposes another barrier. Beyond this boundary, light has not had time to reach us, rendering vast regions of the cosmos forever inaccessible. And then there is the concept of infinity. It is both a tool and a torment for the human mind. Anaximander, one of the earliest philosophers to ponder infinity, posited that the universe was boundless. Later thinkers like Zeno of Elea grappled with its paradoxes, questioning whether motion itself was possible within an infinite framework. The advent of calculus by Newton and Leibniz provided a practical approach to handling infinitesimals, yet the philosophical conundrums of infinity persist. Mathematicians like Georg Cantor revealed that there are multiple infinities, an infinite hierarchy of sizes of infinity, but this mathematical elegance only deepens the mystery when applied to the physical universe. Modern cosmology introduces infinity in even more perplexing ways. The theory of inflation suggests that our universe is but one of countless others in a vast multiverse. Each universe within this multiverse may possess its own distinct laws of physics, particles, and forces. If the multiverse is infinite, as some theories suggest, then every possible configuration of matter and energy must exist somewhere within it. This includes an infinite number of worlds identical to our own, and an infinite number that differ in every conceivable way. Such a framework defies human comprehension and introduces the measure problem. In an infinite set, how can we assign meaningful probabilities or make generalizations about the nature of reality? Even if we were to transcend our current limitations, developing the ability to traverse the multiverse or access its hidden dimensions, we would face the ultimate challenge of infinity itself. The task of exploring an infinite multiverse would require infinite time and resources. No matter how far we journeyed, how much we discovered, or how sophisticated our tools became, the fraction of the multiverse we could explore would remain infinitesimally small. The pursuit of knowledge in such a context would become an eternal endeavor with no hope of completion. And yet, the limits of infinity are not confined to the vastness of the cosmos. They are woven into the very fabric of existence. At the smallest scales, the quantum foam, the seething, turbulent underlayer of space-time, represents another frontier where knowledge reaches its limits. At the Planck scale, our understanding of physics breaks down, and space-time itself becomes a roiling chaos. Beyond this scale lies a realm of speculation, where our theories may no longer hold sway. Thus, the ultimate limits to knowledge are both practical and philosophical. We are constrained by our biology, our tools, and the very structure of the universe. We can imagine overcoming some of these barriers through innovation and ingenuity, but others appear insurmountable. Even if we were to achieve perfect understanding within our observable universe, the infinite expanse of the multiverse would remain beyond our grasp. And so, we are left to ponder, is the pursuit of knowledge an endless journey, one that reveals ever more profound mysteries, even as it underscores our limitations?